All right. I think last time we finished up radical chemistry, and what we decided was there was only one reaction essentially, or two reactions that were of synthetic practicality. And so really at this point for organic chemistry 1, we're starting to come to the end. And what I want to do is I want to make sure that we have this discussion about the next section in the text, or at least in the course, where we specifically talk about synthesis and retrosynthetic analysis. And so this is a skill that is difficult to learn because it's a little bit more than just memorization. You have to know the reactions. That's certainly true. You have to know the reactants and the products and the reagents and how to get from one to the other in order to be good at synthesis. This is a prerequisite. But there's also a little bit of skill in learning about how to think about a synthesis problem. And so I know that we've been doing synthesis all along, and we've introduced these ideas up to this point. But what I want to do now is sort of review it and kind of like make sure that we put it all together in one place. Moving forward after that, we're going to go into talking a little bit about alcohols. And again, remember, we're not going to go through the entire topics of alcohols, but we will learn at least one reaction that's very important, and that's the Grignard reaction, in order how to, it's another way to make carbon-carbon bonds without using alkynes. And so without any further ado, let's go ahead and start this business here. Let's go in. Okay. All right. All right. So the first idea is something that we've already been talking about. And I guess I want to make sure to point this out. And that's that the simplest version of a synthesis problem would be for me to give you a reagent and then give you a product and say, how do you synthesize that? What are the steps to accomplish this transformation? And so this is a one-step synthesis, because this reaction can be accomplished with one set of reagents, or at least one reaction that you know of. So what do we have here in the products? We have an alkyl halide, specifically a bromide. What sort of is the regioselective outcome of the reaction that happened? Well, that bromide got added in the least substituted position. So that's an anti-Markovnikov addition. And so we only know one reaction that accomplishes this transformation, and that's hydroboration oxidation. So BH3, THF, hydrogen peroxide, and sodium hydroxide. So all of these reactions that you can do that are essentially one step would be classified as one-step synthesis reactions. So we could make up all sorts of different possibilities. We could say, what about something like this? Here's a one-step synthesis problem that involves reactions from chapter 7. What's going on here? Well, you did form a new carbon-carbon bond. It's a nitrile. So it's a C-N triple bond. You replaced a bromide, and so this is a substitution reaction. You see that the bromide is in a primary position. The cyanide added at the same location. And so this must have been SN2 substitution. So you substituted the bromide for the cyanide. We could also do something like that when we do another reaction from chapter 7. Some sort of elimination reaction where we take an alcohol and we convert it into an alkene. This is also a one-step synthesis problem. How do we do that? Well, we used concentrated sulfuric acid, and so that'll accomplish that transformation. So these are all examples of one-step synthesis problems, and I think at this point, certainly it is my hope that you guys have been practicing synthesis, practicing your reactions, both in the sense that you could have a reagent like this and say, okay, well, what's the product? But also in the sense that you have a product and you say to yourself, well, what are the reagents that accomplish that transformation? And so I think at this point, this is something that we've been doing a lot of, that you should have been doing a lot of practice with. And the idea of a one-step synthesis problem should be well established in your mind at this point. But at the end of the day, what we have to really focus on are multiple synthesis steps. Problems that involve 2, 3, 4, and even 5 and more steps to accomplish a particular transformation. So one of the ways that we can classify these types of synthesis is to think about, well, how can I accomplish changes in functional groups? All right, so how could I accomplish changes in a functional group? So one example might be, well, if I have a bromide and I want to convert it to another bromide, but move it to another location. So in this case, I have a bromide that's in a less substituted position, and I want to move it to the more substituted position. So how could I accomplish that transformation? Can I do it in one step? Well, the answer to that question is no, I can't do it in one step because I don't know any reactions that in one step move a bromide from one position to another. So this should give me an indication that it's going to take me more than one step to accomplish the transformation. And this is where I'd like to introduce this idea of, again, of retrosynthetic analysis. It really did take, again, I've said this before, but it took me a while to sort of kind of believe in this particular method of problem solving. But I think it finally, I finally was convinced that it is a powerful way to solve synthesis problems, especially when you can't immediately see the solution in the forward direction. If you see the solution in the forward direction, then great, just do it. But certainly for the more difficult problems, you're going to run into this situation where you don't see that solution immediately, and you'll want to use this method to sort of sort out your thoughts. And so let's kind of deal with it in that way. So if I were to think about how do I make this product, and I don't really care what I make it from. What I want to do is I want to figure out what reactions I know that makes that functional group from anything. And so we have to examine the product and figure out what it is and what its properties are in order to make that consideration. And so what do we know? It's a bromide. We know a couple of reactions that make bromides. We could do a substitution reaction to make a bromide. We could do some addition reactions to make bromides. But at the end of the day, that's about all we know. We know some substitution reactions, and we know some eliminate and some addition reactions. Well, let's start off with elimination. What do we know from elimination? Well, we know two different ways to add bromides. We know how to add it anti-Markovnikov, and we know how to add it Markovnikov. And that's when looking at where the bromide is attached is important, because that helps us decide which one is which. So let me just pause real quick, because someone made a point that is the screen a lot smaller than it usually is?
Yeah.
All right, so hold on a second. Is anything I'm doing changing the size of the screen for you right there?
No.
Let's just see if this changes it, because it certainly looks the same for me. There's nothing different about it to me, because on either one of my devices. How's that? Is that any different? Well, short of literally stopping the session and starting over, can I decrease the marker size? Yeah, I can decrease the marker size just a little bit. I mean, okay, well, let's see if we can go from here. So I apologize about any issues that you might be experiencing with it. All right, so what were we talking about? All right, we were talking about elimination. We were talking about how do I make this particular bromide. Did I say elimination? Uh-oh. Did I write elimination but say addition in my mind or out loud? These are addition reactions. So let's review. We know how to do this with addition reactions. We can do it via addition or substitution. We're specifically talking about addition reactions right now. It's the addition reactions of a bromide in a Markovnikov and anti-Markovnikov fashion. We look at the substrate, or we look at the product that we're thinking about, and we realize that it's the Markovnikov product because of all the locations along the molecule, it's the most substituted. So that means that if I were to do the Markovnikov addition of bromine, I would have to use HBr. And then I have to say to myself, what is the substrate that would have reacted from? And I know that I need to have a double bond to do that addition. And so in order for it to be Markovnikov, then the double bond could have been in that location. Well, it also could have been in that location. And that's certainly a possibility. And at the end of the day, you're going to find that this possibility is not really going to be effective, because how do you know, or how do you make this structure that I have circled? Well, you can make the structure that I have circled from this thing. And once you've realized that you've created a possibility that leads you back to the product you just came from, then that's an indication that the possible reactant that you're thinking of is really the wrong choice. And so I'm gonna let that be I'm gonna let that lie on the table right there where it is, if you suggest a particular reactant and that reactant can be made from the product you just came from, you should discount that possible reactant immediately. That doesn't mean that you can't come back to it later if you get stuck, but if I have the two choices of A or B, I want to eliminate B at this moment, in this first consideration, because B can be made from A. Now, I guess someone should point out that technically A can be made from the product as well. So I sort of just discounted myself. I can make this product that way as well through an elimination reaction. I know that this is sort of the exception that proves the rule, but at the end of the day, let's examine these two possibilities and see why A is better than B. And so let's try this again and let's go forward. Okay, so let's think about B for a second. How can I make B? I can make a double bond in that location as long as I have do an elimination reaction. I can do an elimination reaction. I'm going to erase A for a second. One of two ways. I have already decided that I can do it from the original product. But I can also do it if I have a bromide at the end and do a Hofmann elimination or do a Zaitsev elimination. I can do Hofmann elimination from the original product, or I can do Zaitsev elimination from a different product. So now the question is, how do I keep working backwards in order to try to get to the product that I want to get to? Well, at this point, you see that you have a bromide that's in a position that's further away from where we're trying to go. And so that's one indication that maybe you're heading in the wrong direction. And so the bottom line is that the only way to make the product that we have now, to make this reagent, the only way to make this reagent is back to that guy. And so what wasn't obvious right at the beginning when we first started to talk about B is that we've really now have gotten ourselves into a point where we're in a circle and there is no way out of the circle. And so this is what indicates to us that B is not a good option. When we choose A, and A was the other version, we did decide, look, yes, you're right. I could make A this from that reactant. That's certainly true. That is one direction that could happen. But I have another option for A as well. I have to do an elimination because that's the only thing I know that can make double bonds. Besides reduction, I can reduce a triple bond, but I can't place a triple bond here because a triple bond in that location would violate the octet rule because there's 2 carbons attached there. So that's not going to work out for me. So the only thing I'm left with is an elimination. And as I said before, I can do that elimination, but there is another elimination that I can do. I can eliminate that bromine. And so this is a 2-step synthesis problem, but it required just a little bit of consideration. But at the end of the day, it really is only 2 synthetic steps. This is Zaitsev elimination, so a small non-sterically hindered base would accomplish this elimination, and so something like sodium methoxide would be appropriate. And so let me apologize for any sort of confusion that may bring about. But at the end of the day, it is okay to just try a bunch of different pathways until it really is the way to do synthesis problems until you get used to it. And I know you don't really want to hear this, but especially for those of you that are moving on to organic chemistry too, synthesis is going to be a really big challenge, and that's going to really start to present problems if you don't know the reactions and you don't know how to solve synthesis problems in general. And it really does take a lot of practice. And so blindly stumbling through all the possibilities is a legitimate and certainly a way to practice that, you know, that I'm suggesting that you try until you start to get an intuitive understanding for, yeah, this one's not so great. I'm not even going to write it down, and I'm not even going to analyze it. You need to try everything you can. Once the message that I'd like you to take home is that if you get into a situation where you're stuck in a circle and that's the only option, then you know that whatever product you or reactant that you suggested, that's not the way to go. Try a different one. So let's do another example real quick. Let's pop up something else. What about how do I do this reaction? Well, this is another example of a functional group transformation. We have an alkene and we want to create an alkene, but we want to create a different alkene. We don't know reactions that essentially eliminate, that essentially change the position of an alkene from one position to another. So that means that we're going to have to do this in multiple steps. And so this is another example of, well, there's actually two possible ways to do that. I have to do an elimination. I could have eliminated this guy, or I could have eliminated this one. And if I think about A, then what I realize with A is that the way to make A is through the anti-Markovnikov addition of a bromine from that. And what I realize is that this and this are the same thing. And so this is another one of those examples of now where I'm getting into a circle. And so I probably should say A is not the way. And so then that gives us this consideration. Well, let's look at B. How can I do B? Well, can I do addition of bromine from this position or from this alkane? Excuse me, from this alkene? Well, yeah, this is the Markovnikov addition of bromide from an alkene, and it could have been this alkene that we started with. So I could do HBr here, and then I could do this elimination, however, the final elimination is Hoffman because it's the least substituted alkene. So I know that I need a large bulky base. So something like potassium tertiary butoxide. So that'll accomplish that transformation. So this is another example of a two-step synthesis problem. Okay. Now, I certainly could have done this. What if, let me make a slight change. What if this wasn't an alkene? What if it was an alkane? Can we do this reaction in this way? Well, if I had a different starting material, I would still approach this first consideration exactly the same way. I would say I only have certain ways of making alkenes. I can only make alkenes from eliminations. I can do them from reductions as well, but remember, just like we said before, I can't have that because that's a violation of the octet rule. So I can't reduce a triple bond. So I would end up with the exact same consideration. I would say, well, I can reduce A, or excuse me, I can eliminate A or I can eliminate B. If I got to A, I would still say, well, how do I make A? I would make it back from this original product. And so these two guys are the same. And so this isn't the way to go. I would still then take A out of the running. And then I would come back to B. I would say, okay, well, here's something I can do that isn't leading me in a circle. I can eliminate a bromide from B to form the product that I want. That's a Hofmann elimination. It's the same reagents. But now I have a different consideration. Can I make B from the starting material? And if you remember from chapter 10, I can do this. I would use radical bromination to do this. And that's, how do we do radical bromination? I think that's NBS would be one option. NBS and H nu. That'll accomplish a radical bromination. I think the other option is BR2 and H nu. And so, not HBr. I don't think HBr2. So we can, if we change the original starting material just a little bit and make it an alkane instead of an alkene, that doesn't change the very first consideration that we make in a retrosynthetic analysis. All it does is change this consideration. Could we make B from the original starting material? The answer is still yes. It's just a different reaction, and therefore a different different answer as far as the synthesis is concerned. So that's considerations for functional group transformations. The next major consideration to make when it comes to synthesis is changing the carbon skeleton. And so this means removing carbons or adding carbons. When it comes to removing carbons, we essentially only know one way to do that, and that's oxidative cleavage. And we can do that with an alkene, and we can do that also with an alkyne. Whether or not we do it with an alkene or an alkyne determines what kind of product we get, whether we get ketones or carboxylic acids, but nonetheless, we can lower the number of carbons by doing oxidative cleavage, and that's the only way we know. When it comes to adding carbons, we only know one way to do that, and that's something also from the chapter on alkynes That's using alkanide ions in SN2 reactions to do substitutions of alkyl halides. Right now, this is the only way to do this. By the end of the week, we'll learn one more way. We'll learn Grignard. I probably spelled that wrong, but oh well. But at the end of the day, there's only going to be two reactions that we'll know for at the end of organic chemistry 1 that'll add carbons to the carbon skeleton. We only know one set of reactions that remove carbons, and that's oxidative cleavage. So let's think about some examples of that. What if I have something like this? And I want to make it from something like that. Well, this is clearly a change in the carbon skeleton. I've got 1, 2, 3, 4 carbons in the starting material, and 1, 2, 3, 4, 5, 6 carbons in the final product. Did I count that right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Yeah, and so if you're not counting carbons, then you're doing the synthesis problem wrong. And that is always one of the very first steps that you should make, is count the number of synthesis problems. Well, how can we, so let's think backwards. How can we make this thing? Well, we really only know one way to make alkanes, and that's through reduction. And unfortunately, there is a lot of possibilities for what we could have reduced. To give you an example, we could have reduced a double bond. To give you another example, we could have reduced a triple bond. And in each one of these cases, the location of the double or triple bond could be essentially anywhere. It could be anywhere in that carbon skeleton to do this reduction. But at the end of the day, one of these is going to be a better option than the other. So let's start off with this idea about location, and let's see if we can sort of get rid of some of these possibilities. Because essentially, let me just use a red pen to kind of get at what I'm talking about. I could have had the triple bond there, the triple bond could have been there, the triple bond could have been there, or the triple bond could have been there. Of course, some of these molecules are exactly the same, but at the end of the day, I end up with a lot of different possibilities. Same thing with the double bond. It could have been there or there or there or there. Of course, some of those possibilities are the same, but at the end of the day, there's a few of those possibilities. And so how do I decide which one of those locations is the best location to start with to eliminate some of these possibilities? Well, let's take a look at our starting material. If our starting material already has 4 carbons, then let's think about 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. And let's not try to make the double bond or the triple bond involve any of those carbons. Because at the end of the day, when we change the carbon skeleton, the reactions that we know install pi bonds at the end of molecules. And so let's think about that for a second. Now we're sort of down to a decision between these two guys. Which one of these situations would be better? Well, now we've eliminated the location consideration in the sense that we don't want to try to install double bonds in the middle, or triple bonds in the middle of the 4 carbons that we already started with, because in adding the carbons that we're going to add, that's where we're going to get these pi bonds. And so we've solved the location situation in the sense that we want to have the double bond or the triple bond at the end, outside of the 4 carbons that we start with, because it's going to be much more difficult to install these pi bonds in the middle of the carbons that we start with. So now the question is well, do we want to start off, is A or B the better option? Well, at the end of the day, what you see is that you can make A from B. If you can make A from B, then just start with B. If B is a possible solution to the first step that you're thinking of, and you have 2 possibilities for that step, A and B, and you can make A from B. We could do used a poison catalyst to do a single reduction. Then that means, well, don't start with A, start with B, because that would be an extra synthesis step. So now we've got this possibility. So now we've really narrowed it down. We've narrowed it down to the idea that we should start with this thing, because this is the reactant that involves the least number of synthesis steps, and it has the functional groups in the position that are most helpful to us. Remember, the functional group internally to the 4 carbons that we start with isn't helpful. It leads to more synthesis steps, and starting with an alkene instead of an alkyne also leads to more synthesis steps, because if this thing was an alkyne, then we would have to invoke this one as the next step back. And so we want as few synthesis steps as possible. All right, so now that I've got this particular reactant as my possibility, how can I make this thing? Well, I know that I can make alkynes by doing alkanide ions with alkyl halides. So what would be the alkanide ion that I would have to create? Well, I'd have to use ethyne with a strong enough base to make it into an ion, and that would be sodium amide. Well, what would be and I know that I add that to an alkyl halide. Well, what would the alkyl halide look like? Well, the alkyl halide would have to involve these 4 carbons. So let me rewrite those 4 carbons down. 1, 2, 3, 4, and it would have to have a halide at the end of it. Oh, look what happened. We're there. So I know that if I take my starting material and I react it with the alkanide ion formed from the reaction of ethyne and sodium amide, then I will form this material. And so it's a multi-step synthesis where we've changed the number of carbons by adding more carbons. But one of the things that you have to consider is, well, how do I get this reagent? This is the reagent that I would want to react the starting material with. And so what I want to do is I want to show the reader I know how to make that reagent. And so you can start off by saying something like this. You could say, all right, I'm going to do ethyne and sodium amide and then I'm going to do my starting material, and that leads to my product. And so it's just a different way of showing how to do the solution. It's just you have a feeder reaction. And so you may come in the next day or two, you may come across a situation where you need to make the one of the reagents that you have to invoke in the reaction, and showing a set of reactions that makes a reagent will be necessary. And so that's definitely something that you can do. What about if I take this situation and say, I want to make a ketone, and I want to make that ketone from this alkyl halide. Well, remember, if you're not counting carbons, then you're not doing it right. Here I've got 6 carbons, and here I have 4 carbons. So I need to reduce the number of carbons in the carbon chain. Well, before, remember that we really only know one way to, one set of reactions that does that, that has the ability to reduce the number of carbons in a carbon chain. How do I show this? And that's oxidative cleavage. So I can do O3 and DMS, and I can accomplish this transformation. I have some other side products, and that's the other side product. So the question is can R1 be a hydrogen and R2 be a CH3 group? Because if it is, then I can make it from from the starting material. And so the answer is yeah, I can do Zaitsev elimination with sodium methoxide to form a double bond in this location. Forming a double bond in this location provides this structure A, and I can react structure A with through ozonolysis and do oxidative cleavage, and my side product now is this guy. And it should be fairly easy. And from just as an aside, from an actual laboratory standpoint, it's fairly easy to remove 2 carbon molecules from 4 carbon molecules, as long as their physical properties are quite different. And these two things should have vastly different boiling points. In a synthesis problem, it's totally okay for you to say, if I want to produce a ketone, then the only way that I know how to produce ketones is through oxidative cleavage. And so that means that I might have some other side products. So in general, the idea is to do 2 things when you're doing a synthesis problem. The 2 things that you want to do are count carbons and examine functional groups. If you can organize your thoughts with these 2 things, then you'll know what reactions that you have to use. If you're going to add carbons, then that really tells you that you've really only got one reaction. And then, as we do at the end of the week, another possibility You really only will have 2 reactions to choose from to add carbons. If you're going to reduce carbons, you've only got really 1 possibility. And with that 1 possibility comes the examination of the functional group in the product or the reactants. When you think about the functional groups as well, that also funnels down the number of possible reactions that you have in order to make it in order to become a little bit more condensed in what your answer choices are. Remember, at this point, you have a choice between approximately 35 different reactions, and you want to eliminate those 35 different, or you want to reduce those 35 different reactions down to a few choices. And so counting the number of carbons and examining the functional group changes are what helps you eliminate the possible reactions and narrowing them down. So let's try to put it all together. Let's do one big example, and then we'll pause for a second and see if anybody has any questions. I want to create this thing. From this thing. Okay, so let's examine this and let's see if we can do that. So what's step number 1? Or what are the 2 things we should be doing? We should be examining functional group changes and counting the number of carbons. So is the number of carbons the same? How many carbons do we have in the starting material, and how many carbons do we have in the final product? Well, I've got 1, 2, 3, 4, 5, 6 carbons here. And it looks like I have 1, 2, 3, 4, 6 carbons here. So do I need to change the carbon count? I don't. I don't need to use any of the reactions that involve changing the number of carbons. But I do have to do some functional group changes. And so that leads me to the question about, well, okay, if I'm going to do functional group changes, how can I make this particular product? So I'm going to think backwards. Well, I'm going to talk about a reaction that we've already eliminated because we're not changing the carbon count. But when I use alkanide ions to add carbons, I do end up with a triple bond. So that's not one of the reactions that I want to think about because I'm not changing the carbon skeleton. So since I start with 6 carbons and I end up with 6 carbons, doing a substitution reaction with an alkanide ion in order to end up with a triple bond is not the direction to go. But how can I make this thing? Well, it turns out there's several possibilities, and they all involve elimination. How do we make alkynes? Well, I could make an alkyne from 1, 2, 3, 4, 5, 6 carbons that involves 2 bromines here. I could do it from a reaction that involves 2 bromines here. Or I could do it from a reaction that involves a bromine here and a bromine here. And in all cases, I would use a strong base. Sorry, that's NH2. I would use sodium amide and water to create that. And so now that I've put down all of these possibilities, examine these possibilities and decide which one is the best one to go with. You have 3 possibilities. Is it A, B, or C? Well, at this point, you should be saying to yourself, in the case of A and C, we've got a bromine, or we've got 2 bromines in the same on the same carbon. So those are called geminal dihalides. And we don't know any reactions that create geminal dihalides. The only reaction that we know is the vicinal dihalide. All we know how to do is B. We don't know any reactions that accomplish the addition of bromine on the exact same carbon. So that eliminates the possibilities and it really does get us to this one as the only possibility with sodium amide and water. So from the three, we've eliminated it down to the only one that works, and that's this one. So we do know how to do that one. Okay, well, the next question is, how do we make this product? How do we make the dihalide? Well, we only know one reaction that makes that dihalide, and that's the reaction of Br2 with an alkene. And it would have to be that alkene. That's the only possibility at this point. I'm going to move it just a little bit closer. If we do addition reaction of this alkene with Br2, then we'll form the vicinal dihalide. So that we know. All right, so the question now becomes, can I make, and let me put the solvent here, carbon tetrachloride is needed as a solvent. How do I make the alkene? Well, can I react an alcohol to form an alkene? Well, the answer is certainly I can do that. I have a couple of possibilities. I have one possibility is where I do concentrated H2SO4. And another possibility, and this one is important to remember because sometimes making alcohols into good leaving groups is something you're going to need to do, is I can make the alcohol into a good leaving group by forming a tosylate, and then I can react that tosylate with a really strong base like DBN or DBU, and I can accomplish the transformation that way. And so what does that mean? So now we've got two possible solutions to the problem. So I can list the steps like this. One solution would be TSCl, DBN, Br2 in carbon tetrachloride, sodium amide, and water. That's one set of solutions. The other set could be concentrated H2SO4, Br2, carbon tetrachloride, sodium amide, and water. Either one of those sets of synthesis steps is a perfectly acceptable solution to the original synthesis problem. There will be usually more than one way to solve a synthesis. And so what I want to do is I'm going to stop it right there.